Okay, so I'm going to speak about some work in progress on the Hilbert space.
It's not especially easy to read.
It's not easy to read.
I'm the only one.
Use one of the thicker ones.
Yeah. Thanks.
Yeah, if it doesn't work, I can try and pull this down and talk from my tablet. So if you can't read the back, we can switch modes of presentation. Okay, so Tunil and Priyadarshi are students at ICTS. DeWitt was a student at ICTS until recently and has just left, he's a postdoc at Mandelstam. And Victor is a postdoc at ICTS. And in fact, so Victor will be in the job market again this year. He's really stellar. So a lot of what I'm going to talk about is work done by him. So you should keep your eyes out for that. Okay, so I'm going to focus on two questions. And as I said, this is work in progress, and I would appreciate feedback, especially if it's critical. And you have questions that I can't answer, that would be great. Help us answer these. Okay. So the first question is, what is the Hilbert space of quantum gravity in this area? And I'll explain these questions. I don't expect them to be self-evident. And the second question is, how does holography work? And I'll explain what both these questions are, because neither of these questions is a commonly considered question, although I think that they're extremely interesting and we should spend much more time thinking about them. Because De Sitter in some ways captures some of the complexity of our universe in a way that perhaps the ADS doesn't. Okay. So I'm going to first spend maybe like 10 or 15 minutes trying to explain what these questions mean, and then I'll explain what I propose for the answers. Okay, so the first question is, what is the Hilbert space of quantum gravity in the Sitter space? Okay, so now there's been a lot of work, a lot of discussion of DSCFT. And in fact, a lot of the attention has focused on a specific state in De Sitter space, and that space is called the Euclidean vacuum, and it's associated, also with the no boundary proposal of Hartle and Hawking. And the idea is the following. So you think of the metric of De Sitter space. Okay, so I'll be De Sitter d plus 1. So this is the metric of De Sitter space, and you rotate, this coordinate tau to get a sphere which has this. And then the Hartle-Hawking state is the state that is obtained by doing the path integral on the hemisphere. So you do the path integral in this way. And you define the state as e to the minus r. And this was the proposal that Hartle and Hawking had for how you should look at the ground state in De Sitter. And it's a natural proposal based on how you define the ground state wavefunctional in quantum field theory, which is you rotate the Euclidean space, you do the path integral on the half plane, and whatever answer you get for the path integral with some boundary conditions put on the edge of the half plane. Is the ground state, and so Hartle and Hawking said, this is also the ground state we should use in De Sitter space. And so this is one state on which a lot of attention has been focused. Okay? It's also called the Euclidean vacuum. Now, it's also been proposed that, in a slightly different context, that if you take the state and you evolve it to late times, so you can define the state wherever you like. You can cut the path integral here, But you can cut it here and then try and evolve it to late tau. And the proposal there's also been a proposal that sometimes called the DSCFT, which is that psi of G is Z of G, where this is a partition function of some appropriate CFT. I should put, and this is the state in this iteration. And this is also something that's attracted a lot of attention. And in fact, there are techniques to try and compute this. And one way to motivate this proposal is to do the following: is to recognize that if you look at Euclidean anti-de Sitter space, which has a form of this kind, and this is the EDS radius, which I'll tell you already. And you take Z to I beta, and you take L to I L ds, then this metric becomes the metric of de Sitter. And so the proposal is that, in ADS-CFT, you know that you compute some action in the bulk with some boundary conditions put near z equal to 0. And that action gives you some partition function of a CFT. And that's the same as if you do the appropriate analytic continuations, you'll get some new partition function, which also obeys similar ordered entities, although it's not a unitary CFT anymore. And this partition function you can now associate with the wave function of the universe, which is this psi of G. Okay. And so this is again something that has a lot of attention has been spent on, and this is also what is often used to compute, for instance, cosmological correlators from ADS-CFT, which is yes.
So I don't know how important it is, but maybe this is hidden when you were saying boundary conditions. But
Yes.
What is the important? Which observer is using these theories?
This is this boundary condition. So if you think of de Sitter space, so you just think of the late time slice.
Oh, so
This
you are
is the
thinking
global late time
okay,
slice.
the global one.
It's a global late time slice. And actually, thank you for that question. So this G is not the metric of all space-time. This G is the metric on this Cauchy slice.
Oh yeah, because it defines the
On late time slice. And remember that a wave function, a state is given by specifying an amplitude for this metric on the late time slice to take on a particular form. And so, it could take on various forms. So I give you the amplitude for all of those, and that specifies the state. So this is a global description of what the state is. Okay.
So you stated that you could compute correlators using this dictionary.
Using this, yes.
Yeah, so, well, this dictionary does come in two different versions, right? It comes in this extrapolation dictionary and the source dictionary. And I thought that, and they're equivalent if this is ADS, but in de Sitter, you must use the extrapolation.
I think
and that is exactly what you did not write.
Well, I think it's more subtle. It's the fact that when you compute correlators, so this is perhaps what you're referring to. You see,
I'm referring to the paper by Hartle and Stanford.
Yeah, I know you're referring to paper Hartle and Stanford. So it's important. Yeah, let me say about it. So you see, the wave function is given by the partition function in de Sitter. What that means is the following. Let's take this G and write it as eta plus some h. Okay. In that case, the way you would write this is you would write it as e into h times some 2-point function. So this is z. Plus, and this is a function of x and y, plus h times a 3-point function, and so on. H times a 4-point function, and so on. Now, these guys, these 2-point, 3-point, 4-point functions are the standard correlators that you get in EDS. So G2 is like a stress tensor correlator in EDS. And with the appropriate analytic continuations, with the ADS radius continuation and so on. G3 is like a TTG 3-point function. This guy you can compute whatever way you like. Okay, there's no you can just compute it. You compute it using the extrapolate dictionary, or you compute it by turning on sources and differentiating. This you can compute whatever way you like. But notice that if I now want to compute the 2-point function of the metric, that is not given by G2. particular, if I want to compute now the 2-point function of the metric fluctuations in this state, then what I have to do is I have to compute mod of psi squared and then compute HH, and then I have to integrate over this. So in fact, I would get the inverse of G2 if I compute the 2-point function. If I compute the 3-point function, I would get, I would get G3, and then for the 4-point function, for instance, there are various, I could get G3 times G2 inverse plus a G4. Okay? And you see that happens because to compute the 2-point function or a correlator in the Sitter space, you're doing something slightly different conceptually from computing a correlator in anti-de Sitter space. Okay? So if you're computing a correlator in anti-de Sitter space, you're trying to compute some correlation function in the CFT. Those correlation functions in the CFT go in as inputs into the wave function of the universe in the Sitter space, which is this guy. And then you just take the wave function and you have to do one more path integral, square it, mod square it, and do one more path integral, and that will give you these correlators. Now there's another way to compute the same quantity, which is to do this Weinberg in formalism, and that's maybe a little bit like this, like this extrapolate dictionary. So in the Weinberg in formalism, when the cosmologists did this, they don't care about EDS CFT. They said, we'll just define some vacuum. In fact, the way they define the vacuum is in this slice. And we'll go forward and compute the expectation value of the product of two HHs. And of course, that's completely equivalent to doing this procedure, computing first this ADS thing and then analytically continuing, and then doing this path integral, or just doing this in formalism. Okay, so depending on what you're good at technically, you can do either. Other question?
Is it Weinberg, not Schwinger?
So there's a story about this. So Weinberg gave a talk about this at Coleman's conference. I don't know if you were there.
No.
So the first time Weinberg described this was in a birthday conference. Coleman was retiring, and I did a conference, and famous Nobel laureate said, I did it before you did. The Nobel laureate had just also explained why they should have got also the 2004 prize. And Weinberg said, yes, but actually Schwinger did it before I did first. So indeed, I don't know if you, Okay, yes, sorry, you mentioned,
Yeah, so if you want to define the problem in real time, would you not have to also specify this something on this space like model?
This is an S3. So these things are identified. Yeah, so if you have an S8 de Sitter 4, you have an S3 or you have an SD in general. So you're looking at the wave function and you have some fluctuations. So this year it's a closed universe globally, and then you have to specify what you identify these things.
So what are you mentioned a couple of ways of computing G2 and G3.
G2 you just one way is you take this and then you just square it and compute HH, and then you get G2 inverse. G2 you can compute in ADS. G2 is a stress tensor correlated ADS. All the Witten diagram techniques that you have. What Finn was referring to is that there are two ways to compute ADS correlators. One is you take bulk ADS correlators and take them to the boundary. The other is where you never turn on a non-normalizable mode. You only work with normalizable modes and you turn them on, switch them to the boundary. The other is you turn on a non-normalizable mode, you compute the partition function, and then you differentiate with respect to the value of the non-normalizable. So one of them is called the extrapolate dictionary, and the other is called the whatever. It's the traditional Witten, group server.
No, my question was basically the extrapolate dictionary. Why is it? I mean, if you think of this as an extrapolation of correlation functions that you compute in the Sitter space, and then you are taking them off to let's say the boundary, why is it not the same as this cosmological correlators?
It is. This is the cosmological. This HH is in the end a cosmological correlator.
Yeah, that one is, but that is different, right?
The G2 is different.
Yeah.
This is an ADS correlator. This is the coefficient of the wave function of the universe that appears. If you want to compute a cosmological correlator, you have to compute this quantity, which is distinct from the quantity that appears in the exponent here. This is a cosmological correlator.
Yeah, that's the cosmological.
And this is, so the question is, how are ADS correlators related to cosmological correlators? This is how they're related. You compute an ADS correlator, you plug it in, you get the wave function of the universe. Then you square the wave function and you do one more path integral, and then you get cosmological.
I have one more question.
Yeah.
So, in principle, this is like an overlap of two wave functions that you're creating at the initial slice and going forward in time.
What is overlap? Sorry.
of two wave functions on this null geodesic surface, or null surface, where you create something in the initial time and it propagates
Overlap, I can quickly overlap.
initial data on the, then it propagates on along.
Yeah, the initial data here is always taken to be the Hartle-Hawking state. So this wave, in fact, that's
Yeah, I understand that. So suppose if you make some changes now
yes.
in this Hartle-Hawking wave function, is there a way to decipher how it?
Excellent. That's the point. Excellent. Very good. Thank you. So exactly as Ryan asked, I had
Sorry,
just
one more
question of yeah.
One more question.
Yeah.
I mean, that is the only way you can compute T, right? I mean, by taking the extrapolate limit of this.
I mean,
because there is no.
You want to
really,
compute
there is no
this
CFT that is there.
This is
only
an
way you can compute.
ADS question. How you compute TT in ADS?
Okay, but
This
you have to have a CFT to compute it using the source.
If you're just computing it in the bulk, even then there are two ways to compute it. One is you turn on a non-normalizable mode.
Yes.
You compute the bulk action with certain boundary conditions for the non-normalizable mode. Then you differentiate the bulk action with respect to a value of the non-normalizable mode. The other way is you compute a bulk Green's function with only normalizable modes turned on, and you take the points of that Green's function to the boundary with appropriate scaling, and those two things will give you the same answer. I mean, that was the point of this Hartle answer.
I guess my question was that is there a particular CFT that you have in mind that will give you these coordinates?
These things?
Yeah.
So in this, these are all bulk computations. So there's no
Okay, so
boundary
you will not
CFT that is being done. These are all bulk computations. And remember, when you go from here to here, you also have to do this analytic continuation. So you have to put in factors of I. And so in fact, this CFT that appears in De Sitter will have like an imaginary central charge.
Yes.
So it's not a CFT, not in any way a real CFT.
Yeah, that's what I was trying to get at. I mean, when you say that there is a correspondence, it makes sense only if you define what this other side is.
Yeah, so the other side is which I will try and define.
Okay.
It's something which obeys the ward identities of a partition function of a CFT, but is not necessarily a unitary. In fact, it is not a unitary CFT. It's just some object which obeys the ward identities of a partition function of a CFT. Okay, good. So as I said, we're spending a lot of time, and there's so much literature on this. But in the end, guys, this is one state, right? All of this board is about like one state. And surely we don't want our theory to have one state. This is the Hartle-Hawking state, and we can keep computing things in it till kingdom come. But this is not the only thing in the universe, hopefully, right? And there are other things that we should talk about. And the question I want to ask, the first part of this question is, what are the other kinds of states you can have in De Sitter space apart from this one state which is the Euclidean vacuum? How do you modify it? Right? Which is exactly what the question is about. Okay, let me give you the known partial answer to this question. Okay. So this is, I'll keep this one state for now. Okay, I said a lot about the Hartle-Hawking state, but in fact, it is not the only thing which we want to ask questions about. So now, people have thought about how you can modify the Hartle-Hawking state perturbatively. Okay, what are the kinds of perturbative states you can have? In fact, it turns out that the kind of perturbative states you can have in De Sitter space are already pretty tricky. And the reason is the following. You see, let me try and give you a quick argument. The reason is, remember, in gravity, there's a Gauss law. The Gauss law tells you that if you have some mass here, you can measure it out at infinity. So gravity has a Gauss law. Okay, good. But now, fine. So that we know that, and we know that if you're in asymptotically flat space, there's an ATM Hamiltonian that measures the mass for you. But now in De Sitter and in ADS also, there's a boundary Hamiltonian that Finn and others were elaborated the details of, and you can get this boundary Hamiltonian ADS. But now in De Sitter we're in some trouble. The reason we're in trouble is because, as was already asked, this slice in which we're trying to define the state is actually a closed universe. So now, what this tells us is that if you just impose the Gauss law, just the Gauss law, implies that states must be invariant under GDS, which is the symmetry group of this interface, SLD1. So just imposing the Gauss law tells us that the states must be invariant under the De Sitter symmetry. This is not something something which should be very surprising, right? If you do electrodynamics, you do gauge theories. You do it on a sphere, you have to impose the Gauss law. The Gauss law tells you the states are invariant. Now, in the classical theory, you can, all you're trying to do is impose that the expectation value of these charges is 0. But in the quantum mechanical theory, you really need to impose that the state that you have is invariant under all the de Sitter symmetries. Now, if you think about it, the de Sitter symmetries here are SOD1. You can ask, you can try and say, well, I'll do a Fock space quantization. I have the Euclidean vacuum. The Euclidean vacuum is indeed invariant under DBS. Okay, so 0, this is the state we are talking about, is invariant. And then I might say, well, I have a scalar field, I find some creation, annihilation operators, I quantize things, I start acting on it with something, maybe I act with some creation operators. And then you'll find that no such state is invariant under the de Sitter isometries. So we are in trouble because it looks like we have one state which is invariant under de Sitter isometries, and no other state is invariant under de Sitter isometries.
Sorry, but why should we have it?
Why should?
If there's a gauge constraint?
Yeah, it's just a Gauss law constraint. It's the fact that even if you're looking at weakly coupled theories, when you take the limit, if you have some gauge theory, and you try to switch off the coupling, even then, as you switch off the coupling, you should still impose the Gauss law to get a good limit. So if you take a theory of gravity on de Sitter, and if you're doing quantum field theory, that's no problem. But if you take a theory of gravity on de Sitter, even if you look at the limit where G Newton goes to 0, you should still impose the Gauss law constraint. And the Gauss law constraint is that the state should be invariant under the isometries of the space in this weak coupling limit. I'll tell you a more precise thing as we go along. And there's only one state.
Ghosts will not contribute to the story when gauge fix them.
But this is just a statement of, just imposing the Gauss law. I mean, we'll discuss ghosts and so on, but at this level, it's just, Fock space computation. And these are global charges, right? It's not like, there's nothing local here. This is what in a space with different boundary conditions would have become global charges. Like, this is what would have been large diffeomorphisms.
So are you saying this Euclidean partition is ill-defined if I put sources? Or?
Well, we'll discuss what you get if you put sources. For now, I'm just discussing Fock space quantization. I'll describe what the solution is. But so if you just try to do Fock space quantization, you'll find that these states are just it looks like at first sight that the states don't exist. Okay, there's a proposed solution to this in the literature. The proposed solution was discussed by Higuchi in 1991. It's not very well known, but it should be very well known because it's a very important proposal. It's also discussed in the appendix of this most recent Witted, Chandrasekhar and Pennington proposal. This is the kind of problem that people like to forget about. So in this Witten, Chandrasekhar, Pennington paper, they forget about this by saying, we'll take this and we puncture it. And then by puncturing it, we'll forget about this Gauss law constraint. We have operators that address to that. But that's kind of avoiding the problem. There is a problem, which is what happens if you're in de Sitter space and you can't puncture things and go back to what we like, which is familiar. And the proposed solution to this was given by Higuchi, and this is what Higuchi said. So Higuchi said we should do something very radical and unusual in de Sitter space. And what Higuchi said we should do is, you take a seed state. Take this state, okay, which is not invariant. By a dagger 1 to n, it's just some random labels. You take some creation operators, you label that. This is the state in the Fock space. You call this seed. You take the seed state, and you define an invariant state. Let me label it with double bars. Which is you just take the seed state, and you integrate over the entire GS, over all of GDS. So you have unitary operators that correspond to the action of these de Sitter isometries, and you just integrate over the whole group. So it would be like saying that you have some Fock space in a theory with SO31 symmetry, and you take that space and you just integrate it over all of SO31. But now if you look at this state is not normalizable. So Higuchi also proposed a norm, which is that phi 2, phi 1 is like phi C2 to U phi C1. Alternately, you could think of this as being the standard norm with between phi 2 and phi 1, but divided by the volume of GDS. So if you just try to take the standard norm between these two states, you see you will get infinity because you have two integrals over this group, okay? And one integral is just going to do nothing, and therefore you get just a volume of the symmetry group out. And so either you can divide by the volume, or you can just remove one of the integrals by hand and do this inner product. Okay? So Higuchi said you should use this modified inner product, and this modified inner product is the correct way to understand the space of states in gravity. Let me point out something interesting. In this space of states, the Euclidean vacuum, which was the original state, in fact does not exist. It's not a normalizable state. Because even though the Euclidean vacuum is invariant under GTS, it doesn't have a finite norm under this, because if you put 0 here and 0 here, then the action of U on 0 is invariant, and so the Euclidean vacuum now has infinite norm. So Higuchi showed that to have states with finite norm, you needed at least 2 particles in the weak coupling event. And so there were states which he could find, and he could show the norm was positive definite. And there are these nice papers by Higuchi and Marolf and Morrison that discuss this. But this is the proposal for how you should construct the Hilbert space of gravity. Okay. So the question is, what justifies this guess? And I'm going to give you a justification. What justifies this guess? And how is it corrected away from G Newton? Corrected at finite G Newton. Because in Higuchi's proposal, there isn't even a question of how you would try to correct this Hilbert space if you try to work with the full theory of gravity. Okay? This is just a statement for what you should do exactly if G Newton goes to 0. Okay? I'm going to try and answer this question. But this is, when I say what is the Hilbert space of gravity, this is the question I'm going to try and answer. Okay, so this is one question. I know I spent some time with this, but this is kind of important because I felt that the fact that such a question exists is itself sometimes not appreciated, and so I just want to explain this another interesting proposal that exists in the literature, and I'm now going to try and give you this talk justification.
Finite Newton means you're going to include perturbative.
Yeah, at least how do you include perturbative connections, exactly.
States with different particle numbers are
States with different particle number are also, and this norm will make them orthogonal, because the GDS doesn't change the particle number. But states of 3 particles, many of them that you thought were distinct, get identified. Yeah.
Can I not consider coherent states on this space?
You can, you can consider coherent states, sure.
They will also be fine, right?
What do you mean they'll be fine? If you consider coherent states, those coherent states, you have to use the same proposal. Coherent states are just linear combinations of Fock space, so it's not something conceptually new.
Right.
Once you know how to deal with the Fock space, you can consider coherent states.
Just maybe a quick follow-up. Is there a role for wormholes in this?
For wormholes, that I do not know.
That's what I meant. That's why I was asking what you mean by finite.
Am I going to consider non-perturbative connections in G2? No, I have not much to say about that. Maybe the story I described, which I'll describe in some soon, maybe there's a natural way to understand how it works in general, but I will not have anything to say about that in this talk. Okay, the second question, let me spend a few minutes also describing what the second question is how does holography work in DeWitt? Okay? Now, why do I ask that question? That's my question too.
So just one
Yes.
question.
Yes.
When it's in the Hartle vacuum,
Yes.
I can compute various correlation functions.
Yes.
Then isn't it basically that in some sense I am defining these states and computing their own terms?
Maybe it's
If I am doing that, then in what sense all these objections are valid?
You're assuming some kind of state operator correspondence. Before you assume that, you have to define what the Hilbert space is. You're right. There is one state. In that state, you can compute some correlation functions. There's some computations you can do. But you haven't even described what the Hilbert space of the theory is. So to say that you've somehow generated all these states is kind of putting the cart before the horse. It's true, you can compute lots of correlation functions in the Hartle in one state. So it's before you, I think usually when people say that in a CFD, what they mean to say is, look, there's a state operator correspondence. So if I start with the vacuum and I give you all the correlators, I kind of implicitly define everything. But that's assuming there's some nice DNS construction and we know all of those things. And they say all of those things are more confusing.
Or maybe is it that if I just consider only those?
Oh, sorry. What objection? Were you referring to the fact that the Hartle vacuum is non-normalizable?
Yeah.
Oh, that objection. So you're trying to ask in the Higuchi story, how does the Hartle vacuum enter? that is not a question to which the answer is no. It will turn out, as I'll explain now, it's a little bit like trying to define the sphere partition function in string theory. In fact, it will turn out to be almost exactly the same thing. Defining the sphere partition functions in string theory is like making sense of the Hartle state. I'll give you an answer to that question if you don't mind.
When you write this, at what time slice are you inserting these equation operators?
Yeah, so this is a Fock space. So in this Fock space, you don't bother about this. But later, I'll always talk about the date time slice. In the Fock space, you can. I didn't even tell you what these labels were. I was just being schematic. So you could just take solutions of the equations of motion and just label creation operators with respect to those and act on the vacuum. So then you don't say anything about, you have a vacuum. The vacuum is defined by some path integral, but you don't even care about that. After the Fock space, it's just a vacuum, and you act on it. And then you don't say what time slice you act on.
So are you somehow evading this no boundary condition?
What?
This no boundary proposal.
What about it?
So this wave, the modes that you define would be satisfying this no boundary condition.
Sorry. No boundary proposal is just a proposal for defining zero Euclidean. It's just a state. It's a proposal for defining what the ground state of the universe is. I'm trying to ask what are the other states of the universe. So these other states, you could then take the Sitter and try and construct some classical solutions.
Yeah, I was just asking because
those would not be the ground state of quantum field theory.
Chulok and company claims that this low boundary proposal doesn't give you.
Let's not get into that issue. This is an issue of how do you choose the correct contour for the path integral, and and what are the right kinds of contour things you should do. And it's a question eventually of how do you do the Euclidean path integral, because there's some term which has a wrong sign kinetic term. It's not I think of interest for this. I'm not sure if it's of interest. Maybe it's of interest, but I'm not going to have anything to say about that.
So you don't care if it could be non-neutrally safe, you're happy also.
We can write down some wave functions. Actually, I don't even care so much about the if you give me some time. In the end, you can write down some wave functions that are obviously states. Whether they came from doing the Euclidean path integral or not, we really don't care. Or whether they came from doing some heuristic Euclidean path integral, or how you define the complex contour, in the end is not I don't know. What will be? I'm just interested in asking what are the valid states, for which this question is not so much interesting. So other questions? Okay, good. So how does holography work? That's the second question I want to ask. You see, sometimes people say this proposal itself, that I said psi g is equal to zg. I should put it here because it's not exactly equal. This is DSCFT, but this can't be DSCFT, because this is a statement about one state. So when I'm looking for some notion of holography, I'm looking for some notion of yes.
Sorry, so just going back to this correlation functions, the cosmological correlation functions. There, the Gauss law, I guess the implication of the Gauss law there would be that there's some super selection rule, that the correlations should vanish unless all of them are together.
Because usually people don't even consider the effects of. That would not be the implication. So unless the operator satisfies the Gauss law, that would not be the implication.
Not unless the operator. That the insertions as a correlator, that it obeys the selection.
It has not so because you can take, let's say you're doing gauge theory, right? Yeah. And I take gauge theory and I take some state which is invariant under the Gauss law, and then I just insert some operator somewhere else, which is not even a gauge invariant operator. I can still compute the correlation function of that operator between gauge and invariant states. And in fact, that's what is roughly doing. No, it will pick, that correlation function will pick out the gauge invariant part of that operator. If I just insert an operator which is not gauge invariant, I could write it as a sum of an operator which is gauge invariant and something which is not. And the part which is not will give you 0. But
it's like this projection.
Yeah, it will do a projection, exactly. But what people are trying to compute in cosmology is just local correlation functions. So they don't bother projecting onto the part that's gauge invariant. They just compute local, it's a QFT computation in the end. And you're right that it's eventually picking out some gauge invariant quantity, but I'll try and make that more clear if you But they don't bother doing this, separating it into the part that is. Okay, good. So let me explain how does holography work. So what I'm trying to look for in holography is a notion of holography of information. In the following sense, let me remind you, in anti-de Sitter space, we find that there's one thing which is to say that you have you can compute some partition function on the boundary and match it. But there's something which I think is more interesting in the sense of holography, which is that if you put some excitation or some insertion here, then you know in the CFT, or in fact you know on the boundary of ADS by making some measurements here. If you can see, my drawing is not too good, but you're sitting far away, so you can imagine I did an excellent drawing of these observers who sit at the boundary of ADS. And these observers sitting at the boundary of ADS can make observations to determine what this excitation is inside. And in fact, as we've recently shown with many of the same collaborators, you can argue for this using the constraints of gravity, not without assuming to start with ADS CFT, but you can argue using the constraints of gravity that the right kinds of gravitational observations at infinity can determine for you what's happening inside ADS. And there's an analogous statement in flat space, which is if you think of flat space, then observations near the past boundary of future null infinity, sometimes called I plus minus, are sufficient in a theory of gravity to determine what happens on the rest of the boundary. These might be very complicated observations. It's true that these observers, if they waited for some time, could wait for light rays to emerge from these excitations and determine what's happening, right? But nevertheless, in a theory of gravity, by making sufficiently complicated observations, they can know what's happening here. And what is more, you can argue for this starting from gravity. Same in flat space. Okay. So what I'm looking for is some notion of how quantum information is localized unusually in a theory of gravity in ADS.
So
we know that
the whole boundary and not talking about. You're taking the whole boundary and not talking of some entanglement edge.
Yeah, I'm taking the whole boundary. That's the simplest version. You could talk of smaller subregion dualities. So the question is, I'm looking for how is it that gravity localizes information unusually. How does gravity, or how is gravity special? Gravity special in localizing quantum information. Okay. And it is special. And that's really important. And sometimes people try to convert gravity into quantum field theory, and they do, we try to do many things to say, well, gravity is eventually a quantum field theory, and in some ways it is. But the interesting aspect of gravity is the way in which it is different from quantum field theory in the manner in which it localizes quantum information. And I want to ask in the Sitter space, how is gravity different? In ADS, we know how it's different. It is different because you don't have locality of information strictly. You put something here, you're forced by the constraints to make an effect near the boundary. We know the answer in flat space. The question is, what's the answer in the Sitter space? So there's no boundary. So where is the information available? Okay. So now, since I'm running a little slow, what I'm going to do is, I'm first going to try and explain what the proposed. So I hope this question is clear. Okay? So I don't consider this as a statement of holography. This is a statement about the wave function of one particular state. A statement of holography has to have something to say about how gravity localizes information. Unusually, in what way is information localized holographically in the Sitter space? Now there is a proposal that has this spin it, which is the proposal of static patch holography. About which, in fact, I will not have much to say. What I say is not inconsistent with static patch holography, but nor does it obviously support static patch holography. And so it will be nice to understand the issue. The proposal of static patch holography is that if you think of information in this static patch, let's call it 1, this information is available at this bifurcation surface. Okay, so an observer at the bifurcation surface can determine what's happening inside. So I'll say something slightly different. And maybe it's consistent with this. But this at least is not holography. So I want to answer, I want some justification for some argument like this. The justification for this argument, of course, comes from, just looking at the entropy of De Sitter. And saying that, you look at the entropy of De Sitter, and so you look at this point where the De Sitter horizon bifurcates, and with some analogy with black holes, you can argue that the information is there. But I'm going to try and look for a more robust argument for where the information is in gravity. Okay, good. So now, let me explain what the proposals I'm going to make are. Okay, and then I'll say something about the technical details. But if I can make the proposals clear, then that's at least partial success. For those of you who are interested, I'll explain the details and whatever that. I guess we're not super strict about that. I'll try not to be working. Okay, so answer the first question. Okay, this is the proposal. Is that all states are of the form psi of g. So all states, by the way, are given by wave functions. This is the wave function on a late time slice. G is metric on a late time slice. So if I tell you the metric on a late time slice, that specifies the state. Specifying this metric doesn't help you answer questions of what happened earlier in de Sitter. If you want to ask what happens when the de Sitter was as small as it could be, you have to do some calculation. Here I'm just telling you what the state is, meaning what the wave function is in a late time slice. So the claim is that all states are of this form, okay, where S is universal. I'll tell you what S is. Universal. And Z of G obeys the Ward identities of a CFT partition function. And what this means is that it's diffeomorphism and it's Weyl invariant. Okay, Weyl invariant up to a possible Weyl anomaly in given dimensions. Up to which I'll specify, up to possible. This possible. In fact, this is imaginary Weyl anomaly. Okay. So basically, states are. If I look at mod of Z of G squared, that's just genuinely diff and Weyl invariant. Okay. So mod of Z of G squared is just diff and Weyl invariant. Okay. So what is different about this proposal from what I said earlier? I'm saying all states are of this form. I'm not saying that the Hartle-Hawking state is of this form. The Hartle-Hawking state is of this form, where Z of G is some specific thing. But I'm saying that all valid states, all allowed states in de Sitter are of this form. Okay? And you can take, there's no unique Z of G. So in some sense, the space of states in de Sitter is like theory space. Okay? It's like the space of possible partition functions you can write down, subject to diff and Weyl invariance up to a possible Weyl anomaly. It is possible there are additional constraints on the kinds of Z of G that are allowed, but we don't know what they are. Possible that Z of G is additionally constrained. Okay, we don't know what they are. Okay, so notice this is quite different. It's the statement that that all states are of this kind. And notice the statement is just manifestly false in a quantum field theory. In a quantum field theory, it's just not true that all states you can write down are of this kind. Okay, if you just take quantum field theory, I can write down whatever state I like. It doesn't have to be diff and Weyl invariant. Maybe the Euclidean vacuum is diff and Weyl invariant, even in 50, but not all states are. Okay. So this is the proposal.
I'm still not entirely persuaded.
I haven't given you a reason. I'm just
No. But even about the way you're setting up the problem about the vacuum, that this statement that you were doing something much more general because you have all states like normally if you consider this vacuum, it's barely anything. Well, I mean, so then that's the question you said, okay, operator state correspondence. But I would say what we normally do is that in vacuum, when we have all correlators in vacuum, then we by factorization can determine all states. We have an LSZ type kind of construction in flat space, like of course S matrices.
There's an S matrix here.
And in cosmology, though, there is a set of correlators, and those they do in fact satisfy some cutting rules that are reminiscent of what you would use for S matrices. So therefore, I would say that the standard thing with just the vacuum should give some kind of prescription for what a spectrum is, and it may or may not agree with yours.
Well, the vacuum gives you, I don't know what to say that. You're right, you can compute some correlation functions in the vacuum. But to go to that, to the Hilbert space, you need much more. I mean, you're right. If you had some S matrix, so you had some sharp conditional
and correlation functions that satisfy spectral decomposition rules.
Your correlation functions, if you wanted to get the Hilbert space, so you wanted to determine what the Hilbert space is. I don't know of any way where those correlation functions have been used to say these are the states in the theory. There's been no. So the attempt is that the existing state of the art is that you use the Higuchi space to say these are the set of states in the theory, but not to say that and in particular, the question that Anne asked earlier, that in the absence of this, you might have thought that you could consider other kinds of states, not just a vacuum, but you could try and compute correlation functions in other kinds of states in De Sitter. And those correlation functions would be valid observables. But the claim is that those states do not exist. Now, there's nothing from those. So, for instance, let's say I take the vacuum, right? And I activate with some global field object. In a usual, if these were really good observables, I would say this is another state. This is, I act twice with field operators, and that gives you another state. But this state, and then I could say, let me compute correlation functions in this state. But this state does not, in fact, exist in the Hilbert space. Okay. The fact that you can project it back onto the vacuum doesn't tell you that this state exists. Right? And that's the thing that I'm saying. You wouldn't know from the fact that this correlator exists whether this state exists as an independent state, or whether only its projection of the vacuum exists. So that's the new statement.
Your theory could be theory of entirely just a metric or whichever matter.
We could add whichever matter.
You're doing just a metric.
We can do more than just a metric, but in this talk I will discuss just a metric. In general, you could say metric plus meta fields. And of course, there could be additional constraints. I could say, unless you have the entire tower of fields in string theory, this thing doesn't make sense for some reason, but we don't have anything to say about that.
So this factorization of this universal versus non-universal part, is it holds to all others in perturbation theory, or
what factorization, what universal, what non-universal?
E to the power is universal and Z of G is not.
Good. So this is not a, so it doesn't require a perturbative statement, it requires a late time statement. So the perturbative parameter in some sense is the fact that you're an arbitrarily late time, so universals become arbitrarily large. Not G, but just the fact.
But it's actually a perturbative statement.
It's not perturbative, it's just that if you look at the asymptotics, then you can determine what the state is. This is not unusual in gravity. For instance, let's say you're doing flat space. You can do asymptotic quantization at Scri plus in the presence of the Newton's constant. And that's because the large volume of space helps you decouple gravitational effects. So even though the theory is interacting, you can still quantize a theory at Scri plus without doing perturbation theory. And it's similar.
So if you have, say, like Omkar was asking, if you have wormholes that go from past to future.
I don't have anything to say about that.
It's the perturbative statement.
I don't have anything to say about wormholes. You're right. You could say maybe what you're asking is this all ordered in perturbation theory, or do you have anything to say about baby universals splitting off? In fact, you could think of this. Z of G doesn't have to be defined in S3. You could think of this as baby universals splitting off, and that's the question that you're asking. But I don't have so much to say about it.
So that's this Higuchi enough products then generally thought of as just the cosmological correlator, integrated cosmological correlators. They integrate over the cross section.
The Higuchi inner product will come as a redundancy of fixing this different Weyl gauge invariance. You see, the Higuchi inner product is basically saying you divide by the volume of the conformal group. So if you gauge fix this different Weyl invariance to define a norm, you're left with the conformal group. The Higuchi inner product just says you take the inner product and you divide by the volume of the conformal group. And that's
no, but in the
usual
case of correlation, cosmological correlation function of 4 operator insertions,
yeah.
With a 1 cross ratio,
yes.
2 cross ratios. And then is it like you integrate over
the cosmological correlation function of 4 insertions is not necessarily even conformally invariant.
That's why you integrate. That's what I said. So you integrate over those, and then that's like insertion of U in the middle.
No. If you just insert 4 cosmological correlators, like 5x1, 5x4, that is like taking a non-gauge invariant operator and putting it between gauge invariant states, which is something that makes sense to do because that correlator picks up the part of the non-gauge invariant operator which is gauge invariant. So there is a gauge invariant operator that corresponds to 5x1 to 5x4, and then it has a gauge invariant and a non-gauge invariant part. The non-gauge invariant part gives you 0, and the gauge invariant part gives you something. But in fact, as Sandeep and I showed by explicit computation, if you just compute this correlation function, it is in one of these states, or even in the Euclidean vacuum, it is not even conformally invariant. It doesn't satisfy the volume limit, it's conformally invariant. So the fact that the state, the wave function obeys different Weyl invariants is not the same as saying that all correlators obey conformal. Because by inserting the operators, you're picking something. You're breaking something. Okay, good. So that's the first answer I'm going to give. What is the answer of holography? Okay? The second part of the proposal. So this is answer 1. What's answer 2? Answer 2 is that any small range, any any region, any small region of this here, of the lake time slice, has information about the whole. So the statement is that, if I give you, and I'll explain why this is true, even though this correlator is not conformally invariant, if you give me this correlation function in a small region, I can in fact determine the state completely.
Sorry, I just have a nice question here. Does it mean that entanglement wedge can be arbitrarily small?
There's no entanglement wedge here.
I understand, but suppose you can define something like.
I don't know how, this is a De Sitter universe at late time.
So if some analog of this entanglement wedge does not exist in this.
I don't know what that means. Like, what does that mean?
This is a different construct. It's more like taking a sub-region of the boundary and saying, oh, actually, that's the same as taking the whole boundary.
A good one.
But that doesn't work if you have an entanglement wedge.
Yeah.
What do you mean? There's no boundary here. This is a late time boundary. It's not a CFT which is evolving in a Lorentzian space. It's a theory.
No, I understand, but in ADS, if you take some interval, then you have to construct this entanglement wedge and you can reconstruct operators only within that wedge. Right?
Sorry, but what is the relevance of that question to this state? I'm not understanding. I understand that in ADS you can do that, but how is that related to what I'm saying?
No, I'm just saying that it means that there is.
In ADS, the theory of the boundary is.
ADS and DS are fundamentally different.
Yeah, so in ADS there's a big difference, which is the following. In ADS, the theory of the boundary is non-gravitational. In De Sitter space, gravity is generally propagating up in the future. So this state you're defining is a state on a theory of gravity. It's not a theory where gravity has been switched off. So it's different from ADS. There is a way in which you can compute things on the ADS boundary and analytically continue, but the wave function of the universe in the end is a wave function of the metric, which is not something you ever talk about in ADS. You never allow the metric to fluctuate, right? You just define it. So it's a...
No. What?
I mean, in this, you can. But okay.
Okay, it's...
I mean, depending what kind of boundary condition.
If you have metric, you never have a theory of quantum gravity on the boundary of ADS. Here you have a theory of quantum gravity of the big time size. Okay? Maybe we can do different things, but you standard ADS if you don't have a theory of quantum. So this is a statement that if you give me this sphere and I give you something here, it knows about the rest. As you say, this would be a completely crazy statement to make in a quantum field theory. In a quantum field theory, it can't be the case that you give me some region and it knows about the rest, because there's a split property that says you can define the state invariantly here and independently here. If you give me correlators here, I don't know anything about correlators somewhere else. Whereas, I'm claiming in a theory of gravity, if you give me correlators here, you do know what the correlators everywhere are. Let me say this in two different ways, so I can explain.
Takanagi has some talk where he talks about analogs of entanglement wedge in DS, where he takes two states.
Who has that?
Takanagi, where he talks about entanglement wedge. And analog of the entropy, it is a very different definition. It's not really entanglement entropy.
Yeah, maybe let's talk about it later, because right now I'm not understanding where entanglement wedges are relevant here. It's a kinematical statement about states being defined on S3. So the statement is that if you give me this state in S3 and I give you all of these correlations, so I'm going to have to make the statement more precise. The more precise statement is that if you give me arbitrary correlation functions, in fact these cosmological correlation functions, so I'll write a more precise version here. Phi of x1, xn. For xi in any region R, determine psi. I mean, for all xi in any region R, if I give you, and for all possible insertions in any region R, okay, so I have to give you arbitrarily complicated correlation functions, and for all points in a given region, and if I give you that, then that is sufficient to determine what the state is. Notice that, of course, the thing we are going to use here is the fact that the state has this symmetry, right? So in the Euclidean vacuum, for instance, it is true, you give me correlators in one patch, I can extrapolate because there is a scale invariant symmetry that allows me to determine correlators elsewhere. I'm going to say that this is also true here. And as you see, this is different from the way our quantum field theory behaves. Let me try and give you some way to fit it with what we usually know about holography. You see, in holography, one way to phrase holography of information is the following. If I give you a region R, and I give you R bar, whenever R bar surrounds R bar has information about R. That's how holography works in ADS. If I give you a region R and R bar completely surrounds R, then R bar knows everything about what's happening inside R. It's kind of a trivial statement, because if R bar surrounds R completely, R bar includes the boundary. But that's one way to frame it. So you see, but in a sphere, if I take any region, then R bar surrounds R, but R also surrounds R bar because there's no boundary. And that's why, the claim, that's the sense in which you should think of this as being linked to the way in which we understand holography in anti-de Sitter space or in flat space. Which, and both those cases, the statement is, if a region is surrounded by another region, then the constraints are such that information about that region is available outside. But on a sphere, every region is surrounded by its complement and vice versa. So that's the way you should think about this proposal.
Sorry,
Yes.
Perhaps building on this point, but just making sure that,
Yes.
that the way in which I'm trying to
Yes.
figure out what you say
Yes,
matches. So coming back to this crucial argument that you have just made, that R is the complementary of R bar and vice versa because the entire thing is closed. Can I use this, because this was a little bit the spirit of my previous question, sorry. Can I view this as what some people may refer as an operational way of defining what you mean by these states? Because a priori I could have said that since you are taking the global perspective, there is no actual physical observer that can have access. But because of this argument, which is tied to gravity,
Yes.
I could choose R and R bar to be regions that in some, I don't claim to know the full physics of the Sitter, but in some perturbative regime, I may be able to do my quantum field theory construction of linearized gravity, whatever you are doing. So at that level, I could choose R and R bar to be subregions where I actually have an operational way of measuring these correlation functions. So can I take this as a way of, even though you are taking a global perspective, you are now, I could turn around your argument and say, can I use this to actually define why we can make observations?
With some subtlety, which is this fact, in fact, that the fact that these observables are not strictly gauge invariant. So
no, I agree with that.
Yeah, but maybe you can have an operational way to define these observables.
Yeah.
And then the statement would be, indeed, if you define these observables, even though you think you're making measurements in a small patch of space, if you're arbitrarily dense, you know what's happening.
Is that what you're saying?
Yes. But this part of making sense of this operationally is a mathematical statement, but how to make sense of it operationally is an interesting question which we have not understood.
Okay.
It's an interesting
but I agree that when you go to the details, these phi's that I may be mentioning in words right now would not be gauge invariant, therefore this is out of the discussion.
Exactly.
But if you would be able to define it, you could use your argument
you can still define this correlation function, but to define what it means operationally is a more interesting question.
Okay.
How do you do it physically, if you had a lab?
No, thanks, okay.
Yes, please. Yeah.
You introduced that S, and you said S is universal. Could you say something about that S?
This S, in fact, has this S has all of it's something you also compute in holographic renormalization. It's basically the set of counter terms that you get in holographic renormalization with some analytic integration. So that's what this S is. It's something that's been you noticed earlier in ADS. If you try to solve the Wheeler-DeWitt equation, something that Friedel and more recently Alan Wall and others noticed, you get a structure of this kind. But this S basically consists of various local counter terms that you have in holographic renormalization. And it doesn't depend on what the state is. The Z of G is not necessarily a local functional, it could have non-local things, but S is a local functional. Okay, good. So, what do I want to say? Okay, good. So let me see how much I can say.
That's the challenging part of your talk.
Is what?
That will be the challenging part of your talk.
Well,
how to say something with the little time that you have.
Exactly. Well,
Time's up.
I don't know what the time is actually, sorry. I was just focusing on what he was saying.
Okay, if I'm explaining what the results mean, that's all. So let me try and say a little bit more, and then I'll try and sketch how we do the technical arguments. Okay. Let me try and first relate this statement I just made to the statement of Higuchi's construction of the Hilbert space. Okay, how is it that this statement? So let's say you accept this statement. Okay, I'll tell you how we try and derive this statement, and if I have time later. The way we try and derive the statement is, we basically try and solve, all states in the theory of gravity have to obey the constraints of diffeomorphism invariance. These constraints are encapsulated in what's called the Wheeler-DeWitt equation. So if you just impose the Wheeler-DeWitt equation at late times, we show if you can solve it in a certain systematic way to obtain this form of the states. And I'll try and explain if I have time later how this is done in detail. Let's say you accept this for a while. Let me at least make contact with what I said about the the Higuchi Hilbert space and how it is connected. Right? So let me keep the statement here. This is 230 right now, right?
Yes.
Okay, fine. So what is this ZFG? Okay, what form does ZFG have? Let's say you chose to expand G above the flat. Okay. Then, as I said, this ZFG would have a specific form, which is S, as I said, is some form of local terms, okay, which you get from holographic renormalization. Getting what S, the ZFG has some form which looks like this, right? H of X, H of Y. And gx y plus the 3-point function plus 3-point plus h of x, h of y, h of z, x. G4 x y z plus I. Okay, is log of z. You see, now in where, so as I said, ZFG obeys the symmetries of the CFT. What that means is if you look at the log of ZFG, it looks like, you see, ZFG is a functional of h. So you give me h, which is how much the metric is different from eta, and I put it into ZFG, and it gives me a number. This number has the following expansion I can do in it. It looks like h of x, h of y times g of xy, where this g of xy has the same symmetries as a stress tensor correlator in a CFT, plus a 3-point term, plus a 4-point term, and so on. Now the 2-point and the 3-point term are basically fixed. There's nothing, because the symmetries of the theory completely fix them. But the 4-point term can do whatever it likes. Okay, the 4-point term is a function of the cross ratios, and it can do whatever it likes. So there are many possible wavefunctionals of the universe you can write down. And I'm saying you give me the 2-point and 3-point or whatever they are, but you give me a 4-point and a higher point terms. And that specifies for you a state in the Sitter space. Okay. If this is true, then notice I can do the following. Let's say I start with some value of G4. And I consider a different state, which is where I take G4 to G4 plus delta G4. I vary it slightly. Why am I allowed to do this? Because I didn't give you all 2-point and 3-point functions, so I can vary the 4-point function independently. It's like saying in the bulk of ADS, I added an independent 4-point interaction. I would still get some partition function on the boundary that obeys, all the symmetries of a CFT partition function. Okay, it would have some, if you try to decompose it into primary operators, it would have some different 3-point couplings and so on. But at the level where I'm just considering, this partition function with sources turned on for the stress tensor, or in this case the metric turned on, I can vary this G4. So I can consider a state of this kind, and I can consider a different state that's called this psi, which has this G. And this is psi prime, which is everything is the same, except that at least the 2-point and 3-point are the same, but I change G4 to G4 plus delta G. So, because the Hilbert space is linear, I could also consider psi as a function of this G4, and I could consider, looking at a lambda here, so I could consider d psi by d lambda, which is the derivative of this state with respect to this parameter lambda. Notice what that is. That is G4 x, y, z, u times h of x, h of y, h of z, h of u on psi. Okay? Right? That's what it is. I mean, this is an differentiation. Okay? Now, stare at this part. This psi could be the Euclidean vacuum, or it could be some other different wide invariant state. This part looks exactly like a Fock space construction, an action of some operators in the Fock space acting on the original state, but a very specific function of operators in the Fock space acting on the original state. In that, I have taken 4 insertions of this metric operator. I have integrated it with some correlation function of something that obeys the symmetries of the CFT correlation function. and then I act on this state. This by construction, this state by construction is invariant under conformal transformation. So this part of the state, if I just look at this part of the state, it's invariant under the De Sitter isometries because the late time slice realizes the De Sitter isometries in this way. In that if I act on this metric with some late time with some De Sitter isometries, because I am doing this particular kind of integral, I find the state is invariant. You see, and what I did is very simple. I just said, let me write down two different invariant states. One with one value of lambda, one with a different value of lambda. And now let me look at small variations of this state. If I do that, I get this expression of this kind. In particular, if my original state was a Euclidean vacuum, this is now an excitation on top of the Euclidean vacuum. But it's an excitation which has this property that it's invariant under GDS. Okay. So the Higuchi space, this is exactly the space of states that Higuchi constructed. So the Higuchi space is the tangent space of excitations above 0, above the Euclidean vacuum, but you could take any other state to define the Higuchi in those ways. Okay? So the way we should understand the Higuchi construction is very natural from this perspective, in that it is the tangent space of excitations. Okay. Now, I also said, how is this corrected at G Newton? Right? This is what Higuchi said is true at G Newton goes to 0. And the way this is corrected is as follows.
I set up the GHs and so on, you can just specify in any way you feel like.
This one is the 2 point and 3 point you can. But the 4 point you can specify as long as it obeys the correct coordinates.
Okay, so
it's function of the cross
you are
ratios.
closing the coordinates.
So, I mean, it has to be, because
Of course, yeah,
saying the partition function has different values there means these components are made of what entities, but it could be any function of the cross ratios.
Any function of cross ratios, right? So therefore you said, so I didn't get, so the 2 and 3 point function you can specify as you wish.
No, 2 and 3 point functions are fixed by symmetries.
Fixed,
You can't specify.
not for courses, but 4 point you can.
You can change.
So you know dynamical content, you just put it in as...
You just put it in, because any such 4 point function specifies a state. And now you look at the difference of two such states, and that gives you a Higuchi state. So I'm trying to explain where this Higuchi state comes from. It comes from, look at the difference, and it gives you a particular form, which is the integral of this 4 point correlation function integrated with these operators. And this state is exactly the kinds of states that Higuchi constructed. Yes, sir?
No, maybe you have just answered now,
Yes.
but one of the reasons that you were introducing the Higuchi construction is because of normalizability of the states.
I'll
How
explain
do
the
you know-
norm in a second. Right now, it's
Oh,
I'm
so
not
sorry,
writing the
sorry,
norm.
it was not
Right
clear.
now, I just said this is the set of states.
Sorry.
This is exactly a set of states that Higuchi
Yeah,
constructed.
okay.
Now, what are the connections with G? You see, I said I could specify the 2 and 3 point functions.
So tangent space to
Now, the tangent space about a given state. So you take a given state. A tangent space, I just mean you vary the 4 point and higher point correlators in some directions. And if you vary them, you get these kinds of states.
the Hilbert space to begin with is a vector space.
The Hilbert space to begin with is a vector space. Now I'm saying
Now
where
we are
did the
talking
Higuchi...
about tangent space in the vector space.
Well, I'm talking about the space of small... Yeah, you're right. I'm just talking about moving in... it's a different basis. You're right. The Hilbert space is actually...
So
the
this is
Hilbert
a subspace.
It's probably the full space, which is to different bases. Okay, I shouldn't use the word tangent space. You're right. It's a vector space, and so saying tangent space is not such a good thing. But it's a different basis in that rather than looking at a set of all possible G4s, I could instead look at derivatives with respect to
Instead of this exponentiated thing, you want this.
you can pull them down.
Yeah.
Exactly. Now, what are the corrections, the G Newton corrections? They're as follows. I said I could take the 2 and 3 point function, I could specify the 4 point function as I like. Okay, good. But now there are Warden entities that tell you once you've done this, you can't specify the 5 point function exactly as you like. And that is because remember, if you look at a stress tensor correlator,
So it's with Higuchi also had the two particles.
he also had the 2 particle state. Higuchi had the 2 particle state was actually unique. You're right. You can try and change the normalization of the 2 point function perhaps. So you can put some different constants on here, and so you will get exactly one state. So Higuchi had one 2 particle state, which was unique, which is exactly the state you get. And I think one 3 particle state also. You can change because the symmetry is fixed, but the number is not fixed. So you can put a different number here, a different number here. Here you have a large set of states which are specified for all possible 4 points. Okay, remember, let me remind you, if I take a 5 point function, there's a Warden entity which tells me if I take the derivative, I'll get various delta functions like x, delta of x minus y times the 4 point correlator, right? So if I specify the 4-point correlator, I can't really specify the 5-point correlator. There's some constraint in the 5-point correlator. So in particular, if I change this 4-point function, that's not okay to do without also changing the 5-point function. Those things are only important at higher order in G Newton because they necessarily involve one more insertion of the metric. But you see that the Higuchi space, if you go to finite G Newton, must be corrected by adding to these kinds of states, other states. When you change this lambda, you also have to change other terms in the partition function. And the Higuchi state must be corrected in such a way that you get in the end a partition function which is consistent to the what identities. So to really get the Higuchi space, what you should do is you should write down two partition functions, one with lambda here, one with lambda plus delta lambda for the 4-point function, but also the 5-point and all functions corrected accordingly, and then differentiate. So you will get to these corrections. They are not unique, right? Because they are not unique, but you have to add certain specific corrections. There's a choice of corrections you can do, but you have to add corrections so that the whole thing is consistent with the what identities. Okay? So that's one answer to how Higuchi's construction should be corrected.
Okay, can I ask a question? The statement that the generators of the Gauss law also get modified.
That maybe that's a good way to say it. We've not been able to say it in precisely that language. Maybe that's a good way to say it.
So have you checked this consistency which you just described up to which order have you checked this?
There is nothing to check here explicitly because once you have this construction, this is just a statement that all possible states are of this kind. And it's just a statement that if you have a CFT partition function, if you change the 4-point term in that, you have to change also the 5-point and higher point terms in a certain way so as to be consistent with the what identities. I mean, that doesn't imply, that's just a statement about CFT partition functions. So the statement is that states in De Sitter are in one-to-one correspondence with partition functions of a CFT. So the space of states is like theory space. Now in theory space, if you change the 4-point function, you can't say I'll only change the 4-point function and keep everything fixed, because that's not a valid partition function. You're forced to also change higher point functions. And so if you do that, there are various ways you can change higher point functions consistently. But once you do that, you will get the corrections depending on how you change the higher point functions. And you have to add those corrections. So this is something that Higuchi did. Yeah.
So does the particle number commutes with the election of the isometry group, right?
So once you start adding G Newton corrections, probably not, right? Because once you start adding
G Newton correction, that what?
Yeah, these are corrections. The reason they are corrections in G Newton is because the what identity is always relating additional insertion of the stress tensor. So it's always at least one more metric insertion. The metric insertions always come with factors of G Newton. There are no what identities that say if you have a 4-point matter correlator, 5-point matter correlator, those are related. Those are never related. Only that 4-point correlator is related to one correlator with one more stress tensor. Okay, great. So now, what about the norm? Let me answer this question about the norm. Unfortunately, I don't have time to say it in detail. But you see, the norm is the following. How would you define the norm between these different Weyl invariant states? Right? The obvious way to define the norm is you take psi 1, psi 2, you integrate over dg, but you can't integrate over all metrics. You have to divide by different Weyl. So, of course, we know how to do this in string theory. In fact, if you work with De Sitter 3, it's exactly the string theory story. Exactly a string theory story. You fix a fiducial metric. In higher space dimensions, you can't fix a fiducial metric, but you can still fix gauge. For instance, you could fix gauge by imposing some gauge conditions, say flats. But even then, you will find that there is a set of transformations that you have not fixed, and that set of transformations is precisely the conformal group. Therefore, how do you do that? Well, you do that by saying, I will never try to define this norm, but I will only define this norm after I have inserted some of these operators. So let's say I have now my insertion. And now I have some vertex operators which I have inserted. And I also have to do these integrals. And I can use the remaining gauge symmetry to fix the positions of some of these points. Okay? And then I get back my usual norm. This is in fact exactly what Higuchi had. He said divide by the volume of the conformal group. That's exactly what you do here. You fix the remaining symmetry by fixing the positions of some of the vertex operators. And then you get back the norm that Higuchi had. With these corrections that I described.
There are integrals here.
Huh?
There are integrals here.
Here there are, yes. Because, and the reason I integrals is because the wave function always has this form. It's always integral.
No, but there you say you want to fix something.
No, so you write down this expression for the norm, and now you have to insert some gauge fixing condition. So you have to replace some, you have to put in some C course to fix some,
So
get rid of some
remove those integrals.
you'll have to remove some of those integrals. Exactly, and replace them with insertions of C course. Exactly.
Essentially integrate over the conformal modulus.
Exactly. And now the question was, what about the Euclidean vacuum? So you said this is the question I asked in the beginning. How do you define the Euclidean vacuum, the norm of the Euclidean vacuum? Defining the norm of the Euclidean vacuum is basically a question of how do you define this path integral without any vertex operator insertions. It's exactly the question of how do you define the sphere partition function string. If you can make sense of that, you can make sense of the Euclidean vacuum. Okay, I know there's been some work on that, but I don't know. I don't understand well enough. But yeah, this is an open question. If you look at Whitman's recent paper, they will explain it. We don't know how to make sense of the Euclidean vacuum. Okay, we don't know how to make sense of it either, but at least we reduce it to a familiar problem, which is define the sphere partition function. Okay, good. So now, actually, I fortunately said what I wanted to convey. So now let me say one thing about holography, and then I'll say spend 5 minutes on technical. So, 3 issues I read. Okay.
3 issues.
Sorry. Let me 5.
3 issues.
Okay. So okay, good. So the statement about holography I already made. You see, so now if you want to look at genuinely gauge invariant observables, you have to do something of this kind. You have to integrate, right? You have to take this 4-point function and integrate. That's what vertex operators in string theory are integrated over the entire complex theory. But I could nevertheless insert a vertex operator at one point and ask for what that correlation function is. That's a computation that mathematically makes sense. And that's exactly what people do when they're computing cosmological correlators. I could say, I don't integrate my vertex operators, I just insert them at one point. I don't do the integrals or the ZS. And that's something that mathematically makes sense. And so that's what people usually compute, which is these kinds of correlators. Right? But you see, let's say I was given these correlators, even though the physical significance of these correlators is not clear. Mathematically, it's something you can do. In a quantum field theory, it's something you can do. If I'm given these correlators for all xi in the region R, it's clear, and for all n, okay, you have to give me all-point correlator. I'm not saying 2-point correlators fix everything. It's clear that this is enough to fix all of these coefficient functions. Right? Because if you give me these correlators for all, that's enough to fix all of these correlation functions. By the way, the correlators in certain choices of gauge already have, even though they don't obey full conformal invariance, they break special conformal invariance. They do obey scale invariance. You can choose a gauge that they just explicitly obey scale invariance. So it's clear if I give you these regions, for some configuration of points in a small region R, I can scale up that configuration and I can get the correlators everywhere. Okay. And therefore, if I give you this for all configurations of points in a region, I can get the correlators everywhere for any state of this kind. So the fact that the set of states is smaller than it is in quantum field theory, there are constraints that tell you that not all possible states are allowed, tells you that the set of correlators in any region is sufficient to determine what happens everywhere. And let me add more, very importantly, one has to be very careful about the physical interpretation of this. That's because these correlators by themselves, as we already said a couple of times, are not gauge invariant. The gauge invariant observables are things which are integrated over all space. But they make mathematical sense. You can compare the behavior of these correlators in a quantum field theory with their behavior in gravity. In a quantum field theory, these correlators are not enough to determine the state. In a theory of gravity, they are enough to determine the state. And this is the way I claim gravity differs from QFT. Okay, good. So now, I actually said I conveyed the results I wanted to convey. Let me spend just a few minutes trying to explain how we get these, justify this statement, please. And then I can stop.
In conformal theory, those correlators would be enough to define.
To determine the state? No. In a conformal field theory, if I give you correlators in a region, I can do whatever I like somewhere else. Because not all states in a conformal field theory are invariant under the full conformal group. I have states which break the conformal invariance. So the interesting part here is that all states in De Sitter are invariant under the De Sitter group. I mean,
sorry.
So conformal field theory, I specify something there, I can do whatever I like somewhere else. Okay, good. So, how do we get this the tool we use is actually pretty simple. In some sense, this is something that we've done earlier, which is we just impose the constraints of the Weyl-DeWitt equation on the set of allowed states. So the set of allowed states in gravity. So now I'm going to explain why we find Z is e to the is size. So this is the result I'm not trying to justify. If you don't care about the technical justification, I already explained that this is the result. Okay, so that's the result, and now I'm going to give some technical details. And if there are questions, otherwise I can take them around. Okay. You see, the point is that all states must obey constraints, which are called the Hamiltonian momentum constraints. Okay. And they have some form. And the form they have, I mean, there's some specific form that you get, and the form is that H looks like 2 by G by K nil by Ij Gik Gjl minus 1 over D minus 1 by squared minus 1 over twice kappa squared. Kappa here is square root of 8 by G. So this is the form of the Hamiltonian constraint, and this is the momentum constraint. Where this pi here that I'm writing, G is just the determinant of G at G. This pi here is a canonical momentum. So this pi I should think of as just being the derivative with respect to Gi. So you act on the wave function in this way, and the action of this on the wave function should annihilate the wave function. That just comes from imposing consistently diffeomorphism. The Gauss law constraints we discussed are a particular, these are infinite number of constraints because they have to hold at every point. To get the Gauss law constraints, you have to integrate them with the killing vectors, and you extract and then you get the Gauss law constraints. So the Gauss law constraints that we discussed are the subset of these constraints, integrated subset. Okay, good. So now we are interested in solving, these things are impossible to solve. If you just try to solve in general, what this does, this is a hopeless task. Okay, people spend a lot of time trying to solve these things, and they would usually do some mini superspace or something like that, which is not so great to do. If you want to solve these constraints in general, that's very hard. But you know, we have a simplifying feature here, which is we want to deal with this at late times, right? We want to understand the late time behavior. But what is late time? Late time is not good here because not clear because there's no time in these equations. Right? And in fact, this is the famous problem of the fact that in de Sitter space you don't have an external clock. In anti-de Sitter space there's a clock. In de Sitter space there's no clock. So I say I want to look at the late time behavior. What does that mean? So there is an answer to this, and late time basically corresponds to saying that you write Gij as omega squared times gamma ij, the conformal factor times gamma ij, where the determinant of gamma is 1, and late time corresponds to omega becoming universally large. In fact, omega is large, allows you to go to late times and also to early times. So you can also think of a contracting universe. You can break the degeneracy as a factor. You'll get two solutions if you do this, but that's a technical detail. Okay.
Just one maybe stupid question. How do you know that this operator has zero eigenvalue?
You don't. So if it doesn't have any eigenvalues, the Hilbert space is empty. If there's no solution, the Hilbert space is empty. We'll find solutions.
But then, there's a free parameter lambda here. So
it's a cosmological constant.
Yeah.
So if you could show that it exists, the solutions exist only for lambda equal to 10 to the minus 30, that would be solving a great problem.
but I'm saying this thinking is correct for now.
Yeah, if you could show that solutions exist only for lambda, that would be fantastic. But no one has ever done that. It seems unlikely that it would come just from here. There should be hopefully something deeper. But maybe. Yeah. So indeed. So maybe if you're. Okay, great. So now for us, late time just corresponds to omega being large. Okay, good. So if omega becomes uniformly large, by the way, it's important we want omega to be uniformly large. So there are these solutions which are like de Sitter black holes, right? Which have a singularity on the late time surface. We don't want to consider those kinds of solutions. We want to consider solutions of the kind you get in inflation, where omega becomes are uniformly large. And in that regime, it turns out it's possible to solve this equation in the power series in omega. And the trick is you rewrite this equation in terms of this conformal parameter. And if you do that, you find the following equation. This thing becomes something much simpler. It becomes basically 1 by 4d into d minus 1 omega squared plus this lambda by k squared minus 1 by pi k squared into the Ricci scalar and plus some other terms which I won't write because they're not important for what I'm going to say. Okay? Some other terms which are substitutes. This constraint is actually easy to solve. This constraint is just imposing diffeomorphism invariance on the late time slice, but just diffeomorphism invariance in the spatial directions. So as long as you write down a solution that's manifestly diffeomorphism invariance, the momentum constraint is easy to solve. It's the Hamiltonian constraint you need to solve. Okay. So there are some other terms which I haven't written now for lack of time. But let me just explain. If you wanted to solve this equation, how you would solve it. How would you solve it? Well, you'd write down an ansatz, which is psi is equal to e to the I, let me call it t, and t has the form where this is some term which has homogeneity in omega of size alpha minus n, where alpha for now is an undetermined parameter. Okay? So I'm just expanding the solutions in terms of power series in this omega parameter, in this conformal factor. Right? Now you see, what is the largest term here that appears without a derivative? It's this lambda term. Okay? And I forgot some factor here. Sorry. I should have written an omega to the 2. So the largest term that appears here without a derivative is this cosmological term. This is the Ricci scalar term, but the Ricci scalar term is always down by a factor of 1 over conformal factor squared compared to the cosmological term. So this is the term that dominates the largest order term, and you can check that the first, this force is alpha is equal to d, that's the highest order term that can appear, and the leading term basically takes the form root g. With a factor of I into d minus 1 by kappa squared. Root g is also the same as, also known as omega to the power d. So if you just put in e to the I omega to the power d, you explicitly see you will cancel off. But the cosmological constant has some form which is d into d minus 1, the De Sitter cosmological constant. And you see that the derivative of this will explicitly cancel the cosmological constant, provided you put this factor of 5. Okay. This is by the way also the term you get in holographic renormalization. If you are in d larger than 2, then you can check that the next term you get is the Ricci scalar term, which of course, no coincidence, is also the term you get in holographic renormalization. Okay, so this is the next order term. Now let's say you happen to be in d equal to 3, and I'll explain what happens in d equal to 2 in a second. In d equal to 2, notice this term is singular. Let's say you happen to be in d equal to 3. You find there is no further you can go in the power series expansion unless you want to keep terms that are subleading in omega. So in particular, the zeroth order term is just unfixed. Okay, the term which does not scale with omega, see in d equal to 3, this term goes like omega cubed, this term goes like omega, but the zeroth order term is unfixed. But the term that's independent of omega is the Weyl invariant term. The term that does not scale with the conformal factor is the term that's Weyl invariant. So this is the thing that's the arbitrary part of the solution. So you write down the solution, you fix some terms, and there's an arbitrary part. This part is what I was calling the CFT partition function. The reason I was calling the CFT partition function is only because it's different Weyl invariant. So it obeys the same word identities as CFT partition function. What happens in d equal to 2? When this becomes singular, this term is still what it is, but now you find that in d equal to 2, this term now goes like omega squared, and this term is not, it obeys delta P0 by delta omega is minus 1 by kappa squared times omega squared times Rg. Remember, g itself scales like omega squared, so this whole term is like order 1. And in fact, yes. Right. So in fact, if you convert this back to an equation for e to the IT0, we'll find exactly the standard conformal anomaly equation. Is minus I by 2 kappa squared square root g times r times e to the IT0. I'm sorry, it's writing in this small part, but basically, if you look at e to the IT0, this is like a CFT partition function. This is the conformal anomaly equation, but the central charge is imaginary, it's not real. It's in fact what you expect. And you can do this in d equal to 5, and you'll get the right anomaly polynomial. And in this case, apart from this conformal anomaly equation, nothing else about T0 is determined. So this is once again any valid CFT partition function with this right central charge obeys this. If you go to d equal to 5, then d equal this is a 3, yeah. So if you go to d equal to 4, you get the right anomaly polynomial there. But once again, the right anomaly polynomial with A and C central charges being the same. And as long as I give you any CFT partition function in de-Sitter 5 or d equal to 4, which has A and C being the same, that satisfies these constraints. Okay, so that's how we prove these results. That's what S is, and that's why we have this arbitrariness within CFT, and that's why we get the results that we have from. So let me just stop. I'll just summarize and stop since I went over time. Okay. So the question I tried to ask in this talk was, what is the Hilbert space of states, and how does holography work? I said there's a proposed answer to this question by Higuchi, which is an answer that's not well known but should be because it's very interesting. And the claim is that we have an understanding of where that answer comes from, which is that the space of states in de-Sitter space is the space of states of this kind, where Z and G is some different invariant function that can be associated with the partition function of a CFT, not unitary CFT, but a CFT with an imaginary central charge. And you get this form by basically solving the constraints. And what helps us solve the constraints, which are usually so hard to deal with, is the fact that we look at it's like an asymptotic quantization. We look at the form of the constraints in the limit where the conformal factors start. And that gives us these solutions. Once you have these solutions, you also find this other remarkable statement, which is if you look at correlation functions of this kind, I emphasize these are not gain invariant because this operator doesn't commute with the constraints. But nevertheless, this is a mathematically well-defined thing to do. It's something you could also do in quantum field theory. And now you find, for such states, these correlation functions for xi in any region determine R. And the way you should think of it physically is by saying that in all cases, in anti-de-Sitter space, flat space, and now de-Sitter space, if a region is surrounded by its complement, the complement has information about the region. Except that in de-Sitter space, a small region also surrounds its complement, even if the complement is much larger. Okay, so I will stop here and we can take questions. Okay.
So that is also the statement of the holographic principle in a closed universe, right? That sort of the area that bounds some volume contains its degrees of, or contains the information, or the measure of the information content, and if you're in a closed universe.
Fair enough. Yeah, so you're right. If you're in a closed universe, even if you have a region that's very small and another region that looks much larger, in fact, the area of the region around is the same. And so it's not surprising that one has information about the other and the other has information about one. And so it's consistent, except I'm trying to give you a much more precise argument for why it's true. I'm not just making some hand-waving arguments. I'm trying to say it's true for this specific reason.
And another question, yes. So do you have any, this construction of this space of states, does it shed any light on the Sitter entropy?
No, unfortunately not. It would be very interesting to understand where the Sitter entropy comes from, but we don't have anything to say about that. It's an extremely interesting question which we have thought of, but we don't have an answer.
And is that because you're considering this late time slice that doesn't really have much to do with the static patch?
That's correct. That's one reason why it's very hard to make contact with the size, the area of the de-Sitter horizon, because you're considering a late time. If you have a global perspective, so if you want to ask something, but even then maybe there's something one could say about the de-Sitter entropy which.
Let's continue the questions over coffee and pick up again at 3:30.
Thank you.